Section 2 is regarding independent and mutually exclusive events. These are two commonly mistaken ideas. Some folks have trouble keeping these two things straight. So hopefully we can fix that before it becomes a problem. It's important to know that independent and mutually exclusive do not mean the same thing. Okay? Two events are independent if the outcome of one event has no bearing on the outcome of a second event. They're mutually exclusive. Two events are mutually exclusive if they cannot happen at the same time. So by definition, the outcome of one precludes the outcome of the other, right? And mutually exclusive, the event A occurring means that event B cannot occur, so couldn't possibly be independent, right? So these two things are definitely different definitions. So let's start with independent events. Two events are going to be independent if these three things are true. Now, the good thing is if one of them is true, all of them are true. So if you're trying to show that two events are independent, you only have to show one of these. But they are. The probability of A given B is equal to the probability of A, which would indicate that B doesn't have any impact on A. The probability of A is what it is regardless. Or, second point, probability of B given A is equal to the probability of B. Same reasoning there. And then if the probability of A and B equals the probability of A times the probability of B. Typically what we would say is, when we defined this earlier, we said that the probability of A and B is the probability of A times the probability of B given A. But since the probability of B given A is just the probability of B, then we have this new form for the probability of A and B. But like I said, in any in practice, in any kind of problem where you're trying to show if events are independent, you only have to show one of these three things. It's important to note that sampling methods can affect independence. If we're sampling with replacement, then typically these events are going to be independent. These are most helpful to understand, I think, with kind of small sample spaces. So say, for example, you have a deck of cards. There's 52 cards in the deck, 13 of each suit and ranked ace through king. So if I want to know what's the probability of selecting a card from the deck and getting an ace, okay, and then I want to know what's the probability of drawing a second ace. So if I do this on two successive draws, what's the probability that I get an ace and then the probability that I get another ace? Well, if I take the first ace and I put it back in the deck, then the probability for drawing that second ace is no different than it was for the first one, right? That would make these events independent. However, if I take that ace that I drew the first time and I leave it out when I go back in to draw the second card, now the probability of getting an ace is a little bit different, right? Number one, there's only 3 aces now, and number two, there's only 51 cards total. So originally the probability of drawing an ace is 4 out of 52, but if I keep that ace out, that changes the probability to 3 out of 51, okay, which is a slightly different probability. So if we're sampling without replacement, then typically that means that we have dependent events. Now, if the population is large enough, then the difference in the probability is so small that we don't really worry about it. Okay, sometimes in practice, sampling without replacement is kind of necessary, but if the population is big enough, the sample space is big enough, then it's not too big a deal. But just know, technically dependent. All right, so let's talk more about mutually exclusive events. Sometimes, by the way, this is, instead of mutually exclusive, you may hear two events as being disjoint. Those two terms are interchangeable. Mutually exclusive, disjoint mean the same thing. So if A and B are mutually exclusive, that means they can't happen together. They can't happen at the same time. And so the probability of A and B in this case will be 0. All right, we're going to work two examples, 3.6 and 3.10, and we'll do it on our examples worksheet that is posted in Classroom. So hopefully you have that still from the first video, and we'll turn it over to the document camera. In example 3.6, we're flipping two coins. Okay, so we want to try to figure out some events here, independent, mutually exclusive, that kind of stuff. So for part A, well, first of all, let me read the intro. We flip two fair coins. The sample space is HH, HT, TH, TT. Notice that HT and TH are actually two different outcomes depending on what happened first, so we need to list them separately. And so part A says let event A mean getting at most one tail. So sometimes at most, at least can get confusing, but in this case, at most 1 means either 0 or 1, right? We can't have any more than 1. So the outcomes that have 0 or 1 tail would be those three: heads, 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 tails, and tails, heads. Event B would be getting all tails. So there's only one outcome where that happens. By the way, you don't have to put the curly braces around there. I'm doing it because it was in the original problem in the textbook, so just trying to be consistent with that. All right, so the probability of A, in part C, the probability of A will be the 3 outcomes that we have for A divided by the 4 possible outcomes in the sample space. So that's going to be 3/4. Probability of B, since there's only one event, one outcome here out of 4, that will be 1/4. All right, so now C, we're defining a new event here. Let C be the event of getting all heads, so that can only happen one way. That would be heads, heads. So out of A, B, and C, are any of these events mutually exclusive? So we want to think of these as kind of like pairwise exclusive. So in other words, is A mutually exclusive with any other event? And it looks like event A is mutually exclusive to B. So there's not really a notation for this. So I'll just say A and B are mutually exclusive. And then if we look at event B, well, we already know B is mutually exclusive to A, but also B and C can't happen at the same time, right? They're different. So we'd say B and C are also. And then C, we've mentioned that it's disjoint with B, but is C disjoint with A? No, because we see that the HH actually occurs in both. So you could have one event that's in A and also in C at the same time. So A and B are mutually exclusive. B and C are mutually exclusive as well. I'll just write that. All right, event E, I'm defining a new one, is getting ahead on the first roll. So E would have 2 outcomes, heads, heads, or heads, tails. All right, so find the probability of getting at least one tail. We're not asked anything about the probability of E. We're just throwing it in there. Find the probability of getting at least one tail in 2 flips. So at least one tail. So this isn't a sample space that's been defined yet. This is different from event A. So how many outcomes have at least one? So one or more tails. Well, heads, tails has 1, tails, heads has 1, and tails, tails has more than 1. So those 3 would be potential outcomes that would satisfy this event. So the probability would be 3 out of 4, because we had 4 in our sample space, and 3 of them have at least one tail. All right, so that's example 3.6. In example 3.10, we're going to talk a little bit further about independent and mutually exclusive events. So in this scenario, we have a student that goes to the library, and event B is the event where the student checks out a book, and event D is the event in which a student checks out a DVD. So the probability of checking out a book is 0.4, the probability of checking out a DVD is 0.3, and the probability of checking out, oops, this should be a B, not an A, there's a typo. I'll fix that on your copy. Probability of B and D is 0.2, so the probability that a student checks out both a book and a DVD is 0.2. So now, we want to find the probability of B given D. So, remember in the notes from just a moment ago, we have the probability of B given D, I'm adapting it from what's in the notes, is the probability of B and D divided by the probability of D. Okay, so probability of B and D is 0.2, probability of D is 0.3, so 0.2 divided by 0.3 would give us 0.67, I believe. I'll just double check my math there. Yeah. All right, so the probability of B given D, 0.67. So now let's do it the other direction, the probability of D given B. Remember that we shouldn't expect that these are going to be the same necessarily. All right, so this is going to be the same formula except these are turned around, and it will be the probability of B and D divided by the probability of B. So this would be 0.2 divided by 0.4. So the probability in that case is 0.5, or 1/2. All right, so next question. Are B and D independent? Well, B and D, we would know B and D are independent if the probability of B given D is equal to the probability of B, which we can see that it's not. They're different. Likewise, the probability of D given B would be the same as just the probability of D, but it's not. So are these independent? The answer would be no. Are these events mutually exclusive? Well, if they're mutually exclusive, then the probability of B and D would have to be 0. And since it's not, then we know that these events are not mutually exclusive. So this is just kind of an interesting example of two events that can both happen at the same time, and they have an influence on each other. If someone's going to go to the trouble of checking out a book, they might just go ahead and grab a DVD at the same time. Or if they're going to grab a DVD, they might be likely to go ahead and grab a book at the same time. Since they're already at the library, certainly it's going to affect their probability. So that concludes example 3.10, and we'll go back to the slides. For homework, 40 through 43 should give you a decent level of practice for this section. I don't think it requires too terribly many problems, so hopefully that'll be enough. And we'll move on to section 3.3, 2 basic rules of probability. The first rule is the multiplication rule. Basically, this is when we're trying to find the probability of an AND kind of scenario. Okay, the probability of A and B is the probability of B times the probability of A given B. We talked a minute ago about independent events. If A and B are independent, then we can replace that probability of A given B with just the probability of A. The addition rule is what we're going to use when we have an OR kind of scenario. Okay, so this is usually, the multiplication rule is usually when we're doing two things, right? Like maybe we're going to draw a card out of the deck and then we're going to draw a second card out of the deck. Okay, it's two things, two events are happening. With the addition rule, this is typically happening in one event. Okay, so I want to know what's the probability that I draw an ace or a spade. Okay, so the rule changes. Instead of using the multiplication rule, we use the addition rule for OR scenarios, and basically we have the probability of A plus the probability of B minus the probability of A and B. And the reason for that subtraction there is it's possible that A and B could happen at the same time on on any one draw or any one event. So I've got cards stuck in my head. So on any one event, it's possible that you could have a scenario where both happen, A and B both happen. So if that happens, if that's the case, we're counting the AND scenario when we say probability of A, that A and B is built in there. And then when we do the probability of B, the probability of A and B is also built in there. So we have counted the probability of both twice. So we have to subtract that probability of A and B back out again. I think when we work an example together, that will make more sense, and hopefully that'll be cleared up. If A and B are mutually exclusive, then A and B can't happen at the same time. So our addition rule simplifies to just the probability of A plus the probability of B. All right, so here's the example I was talking about. I think hopefully after doing this example, the whole addition rule having to subtract out the and, hopefully that'll make sense. For our third example of this video, we have a college soccer player named Carlos, and we're told that he makes a goal 65% of the time that he shoots. He's going to attempt 2 goals in the next game. Event A is that he's successful on his first attempt with a probability of 0.65. B is the event he's successful on the second attempt, also with a probability of 0.65. And then we're told that Carlos tends to shoot in streaks. So the probability that he makes the second goal, given that he made the first goal, is 0.90. So what is the probability that he makes both goals? So this is an and kind of scenario. We want to know what's the probability of A and B. Okay, sometimes the hard part about solving a probability question is just figuring out what is it that we're being asked in symbols, because we kind of know the formulas for the symbols, and if we can work that out, then the rest of it's not too bad. So remember that the probability of A and B will be the probability of B given A times the probability of A. So the probability that he makes goal B given that he makes A times the probability that he makes A. So now we have 0.9 for the probability of B given A. That's what was given here. He makes the second goal given he makes the first goal, 0.9. And then the probability that he makes the first goal, which is up here at 0.65. So multiplying those together, we get 0.5. Make sure you can see that on the video. 0.585. All right, for part B, what's the probability that Carlos makes either the first goal or the second goal? I think maybe I'm going to move down here so I can have a little more room. This is an or question, right? Probability of A or B. So in this case, we want to do the probability of A plus the probability of B minus the probability of A and B. And the reason for this is the probability that he makes goal B includes whether he made A or not. Right? The probability of making that shot doesn't take into account making the first shot or not making the first shot. So what we want to do here is we want to take the probability of A, 0.65, plus the probability of B, which is also 0.65. And then we want to subtract the and, right? We just found that, 0.585. So the probability that he makes A or B is 0.715. So, part C. Are these events independent? Definitely not, right? The probability of B given A is not the same as the probability of B, right? Probability of B given A is 0.9. Probability of B is 0.65. So these are not independent. For D, are they mutually exclusive? Well, no. In order to be mutually exclusive, A and B, the probability of A and B would have to be 0, right? These would have to be events that can't happen at the same time. So they are not mutually exclusive either. All right. That's it for example 3.15. Let me know if you have any questions. The homework I suggest that you do for section 3 is practice problems 44 to 53. Those are problems that are all single questions about the same topic. So like 44 has you find the probability of C, and then 45 has you find the probability of L, and so they're each one thing. So that may seem like a lot, but it's really not as bad as it seems. And then number 82 is actually a multi-part question involving the casino game roulette. So I don't recommend that you go play roulette, but I think it's an interesting exercise to kind of see what's going on there. So let me know if you have any questions. Thank you very much.